Okay. So, the point of today's lecture is doing better than brute force search for NP-hard problems. So just to remind you, we've been talking about NP-hard problems for a couple of weeks, but we've been focusing on approximation algorithms, where you insist on polynomial time, and therefore you have to relax correctness. So we're looking at approximate correctness always being close to the optimal solution. So this time we're actually going to insist on full correctness. Okay, we're going to ask for algorithms that are always correct. Now, for an NP-hard problem, you don't expect it to run in polynomial time, so you'd like it to run as fast as possible. And at the very least, you'd like to run faster than brute force search. Okay? And again, the first time you sort of learn NP completeness, often you're sort of taught to think of NP completeness as meaning you can't beat brute force search, but reality is a little more nuanced. Okay, so actually there's a lot of problems where there are exponential time that are algorithms which are significantly faster than brute force search, and in this lecture we'll revisit three old friends and see that concretely. So the vertex cover problem, and then the traveling salesman problem, and finally 3-SAT. Okay. So that's the point of the lecture. You can often beat brute force search, and you sort of already know a lot of the ideas necessary to do so. So we talked a lot about vertex cover on Thursday. We're going to talk about it again now. It's actually going to be a special case we're going to look at of where there's no weights. So in other words, the cost of every vertex is 1. So remember, in general, the vertex cover problem, I give you an undirected graph, non-negative costs on vertices, you want a min-cost vertex cover. So here you just want a minimum cardinality vertex cover, where again, a vertex cover is a subset of the vertices that includes at least one endpoint from each edge of the graph. Okay? So same problem as on Thursday, except all costs equal to 1. And actually, we're gonna look at even more of a special case, which is rather than computing the minimum size of a vertex cover, I'm going to give you a target K, and I just want you to figure out, is there or is there not a vertex cover of size at most K? Now, in general, this isn't really that much simpler a problem. If you could solve this problem, you could just run through all values of K and see what's the sort of smallest one for which you can find a vertex cover. So here, the special case is we're going to be thinking of K as small. Okay? So if you kind of like having some concrete numbers in your mind, think of K as, say, like between 10 and 20, and the graph has maybe hundreds of nodes or thousands of nodes. So we want to know if it has sort of like a really nice small vertex cover. Okay? And so for this problem, we're going to do better than brute force search. Okay? All right, so what's the line in the sand? So how long does it take to do brute force search, so the most naive brute force search, to check if there's a vertex cover of size K or less? Like as a function of n and K, what's it going to be roughly? And choose K, that's right. So, so given a alleged vertex cover, it's easy to verify it, whether or not it is a vertex cover or not. So the obvious thing to do is try all possibilities for a size K or less vertex cover. Okay? So brute force is going to be proportional to n choose K, the number of subsets of size K of the vertices, which in the small K case, is basically n raised to the K. Okay? N to the K power. Now, strictly speaking, for any constant K, this is a polynomial time algorithm, but if you think about actually running this, I mean, you can't run this algorithm unless K is super small, like 2 or 3 or something like that. Okay, so even K equal 10, forget it. You could never run this algorithm. Okay, so we want to do better than this. And so just, a comment about context. So this idea of, having an algorithm for an NP-hard problem that runs fast when some parameter is small, like the optimal solution, what you're seeing here is just a glimpse of a much broader field called parameterized algorithms and parameterized complexity. There's a whole course on that topic, CS226, taught here at Stanford, usually by my colleague Ryan Williams. So you can see a lot more examples like this in CS226. So we're just going to have this one example so you can get a taste for it, but know that there's kind of a very vibrant research field around these kind of parameterized running time bounds. Okay, it's been actually quite lively over the last 10 years or so. Okay. So by beating brute force search, what do we expect? What would we like to do? Okay. So what we'd like the dependence on n, the graph size, to be polynomial no matter what k is. Okay, so some polynomial in n. Now, we're not expecting a polynomial time algorithm for all k, right? That would imply p equals np, so there's going to be some dependence on k, and maybe the dependence on k is going to be not so good, like exponential. Okay. But better than n to the k would be a running time bound where the terms involving n and the terms involving k are different, okay, are separated from each other. So in particular, k does not appear in the exponent of n is what we'd like, okay? And again, because we don't expect really sub-exponential time algorithms for vertex cover, we would expect f to be at least exponential in k, although hopefully not worse than that, okay? Or even, NP hardness does not preclude a running time with the form polynomial in the graph size, plus some presumably exponential function of the size of the set that we're looking for. Okay, k. All right. Okay. And so running times, so algorithms of this type, or problems of this type, are called fixed parameter tractable. Or FPT. Okay. So that's a buzzword you can always look up, fixed parameter tractable algorithms. Okay. So for the vertex cover problem, okay, so it turns out there's some problems which seems to admit algorithms of this form, some problems and parameters where you get algorithms of this form, and some where you don't. For vertex cover, I'm going to show you next that we do get a running time of this form, even of this better one. Okay, polynomial in n, even essentially linear in n, plus an exponential function of k. All right? And again, this doesn't contradict p equal np or anything like that, because when, in general in the vertex cover problem, the optimal size of a vertex cover might be big. It might be like n over 2. And so then if f is exponential in k, we're not getting a sub-exponential time algorithm for general vertex cover. We're just doing much better when we're checking for small vertex covers. Okay? So any questions about the setup? Okay. So here's going to be the algorithm. Okay, so again, we're given an undirected graph. All costs are unit. We want to see if there's a small vertex cover or not. So the first thing we're going to do is we're going to look at the degrees of all of the vertices. Okay? And any vertex with degree at least k plus 1, we're just going to put in our vertex cover so far. Okay? So again, we're looking for, say, a vertex cover of size 10. Any vertex with degree 11 or more, we just sort of right up front put that in this set S. And that's without loss of generality. Do you see why? If we're checking for a vertex cover, okay, so if we want to know if there's a vertex cover that only has 10 vertices, and we don't pick some vertex with degree 11, well then to cover all of those 11 incident edges, we have to pick all of their other endpoints. But that would be 11 vertices in the vertex cover, and we don't have the budget for that. Okay? So if there's a vertex cover with size at most k, it must include all vertices with degree at least k plus 1. Okay? So sort of a pre-processing step. So two more pre-processing steps. We've argued that we have no choice but to take all the vertices in S. And that means that we now don't have to worry about covering any of the edges incident to vertices in S. Okay? They're already going to be covered because we pick all of S. So to get the residual vertex cover problem, we just delete the vertices S that we've already chosen from the graph, along, of course, with all of their incident edges. Okay? So all of the edges that we delete, we've already covered. All of the edges that are left in G prime, we haven't covered. So the residual problem is to supplement the vertices in S by a vertex cover of G prime. Okay? That's where we are. All right, so the third step just says, well, G prime, for all we know, after we've deleted all of S, there might be some isolated nodes, vertices with degree 0. Okay? So there's no reason to pick those, right? That just means that all of the edges incident to that vertex are already covered by vertices in S. Okay, so there's literally no reason to pick this isolated vertex. It's totally redundant with our previous commitments in the set S. All right? So just like without loss of generality, we take S. Given that we're taking S without loss of generality, we can remove all isolated nodes from G prime, call the result G double prime. Okay? So now we see how big G double prime is. And if it has more than k squared edges, then we assert that there's no vertex cover of size at most k. So do you see why that's true? So what's the degree of every vertex that's left in G double prime? Well, we removed all the ones with degree at least k plus 1. So everybody left in G double prime has degree k or less. The degree of a vertex is exactly how many edges it covers when you pick it, okay, assuming no redundancies with other people. So each vertex in G double prime can only cover k edges. You're only allowed to pick k of them, okay, given the budget on your vertex cover size. So there better be at most k squared edges. Otherwise, there is no hope. Yeah? Yeah. Okay, so far so good. So now we get to kind of like the real problem, which is G double prime, right? So we have part of our vertex cover S. We need to pick the rest of the vertices from G double prime so that we cover all the edges in G double prime, which is just the vertex cover problem. But it's the vertex cover problem in a much smaller graph. So how are we going to solve it? We're going to solve it by brute force search in the smaller graph. And at the end of the day, we return yes, if and only if G double prime has a vertex cover of size at most k minus s. Okay? And we implement 5 just by brute force search, literally enumerating over all subsets of the vertices of G double prime of this size and checking if it's a vertex cover or not. Okay? So that's the whole algorithm. Okay. So I've already sort of talked through the correctness. So I'm not really going to write anything more down formally. But so just to review, the first claim was that if there does exist a vertex cover of size at most k, it has to include all the vertices in S. So without loss, we can restrict attention to that. Those edges are already covered. So without loss, we can delete all the edges incident to S. Isolated vertices don't cover any edges, so without loss we can delete all the isolated vertices from G double prime. We're correct if we actually halt in step 4, okay, again because with that many edges and such small degrees there's no way you could have a small vertex cover. And then finally, the vertex covers of size at most k of the original graph are precisely S plus any vertex cover of size at most k minus size of S in the reduced graph G double prime, and we solved that by brute force search, so that's clearly correct. Okay. So any questions about that? I wasn't planning on really saying more about correctness. Okay. All right, so what about the running time? So the running time follows from this claim. If we reach step 5, and of course we may not, I guess one sort of edge case I didn't really mention. So it's possible this is negative, okay, if S had k plus 1 or more vertices, but then it's sort of clearly a no. Right, so you need all of the high degree vertices. If there's more than k high degree vertices, then clearly there's no vertex cover of size at most k. Okay, so if this is negative, then just think of this as being an automatic no. All right, so in step 5, the size of G double prime is O of k squared. Okay, first you're saying, wait, this is obvious. It's like by definition. Okay, but what do I mean by size? So definitely the number of edges in G double prime is at most k squared, okay? That's because otherwise we halt. And moreover, remember, G double prime has no isolated vertices, okay? So that actually means with only k-squared edges, it can have at most 2 k-squared vertices. Okay, the sparsest it could be is just a perfect matching on the nodes. Okay, so the size of the graph is k-squared, which means brute force search is just going to be 2 to the k-squared, 2 to the O of k-squared. Right, we pick all subsets, potentially, of G double prime. So the final runtime, straightforward to implement, in O of m plus O of 2 to the, let me do it this way, 2 to the O of k squared. Okay? And this is of the promised form. Okay? So polynomial time plus a function that depends only on k. The polynomial that depends on the input size is as good as it could be. It's linear time. We knew that f was going to be exponential, realistically. Otherwise, we'd have a sub-exponential time algorithm for vertex cover. So, the best exponential, you might want an exponential that's like 2 to the k or even 1.5 to the k. So here we're getting 2 to the O of k squared. Okay? So it's, you'd like that to be better, but still, it's just an exponential function in k. A nice homework problem, so I didn't ask it to all of you this quarter, but a nice homework problem is to use some of the linear programming techniques that we were discussing last lecture, and you can actually get this down to O of k. Okay? So that's sort of a really best case scenario in parameterized algorithms, right? So you get linear time in terms of the graph, and just a single exponential function in terms of the parameter. Okay? And so this is actually a particular type of FPT algorithm. So this graph G double prime that we constructed in fixed parameter tractable language is called a kernel. And the point is that you can take a vertex cover problem on an arbitrary graph as big as you want, and you can reduce it to the same problem on an instance size which depends only on the parameters. Okay, so in this case we reduce it to the vertex cover problem on a graph with only O of k squared vertices. And again, so you get a kernel which is linear size in this homework problem, and so that gives you the 2 O of k. You only wind up doing brute force search on a graph with a linear and k number of vertices. Okay? So this is one way of beating brute force search. Okay, and again, I just want to emphasize, n to the k, which was brute force search, I mean, that's really unrealistic for any problem instance you could imagine. This algorithm, you're not going to be able to solve large instances. It's an NP-hard problem, so it's not surprising. But really, at least it does sort of push the tractability region, quite a bit further past brute force search. Right? So 2 to the k is really much, much, much better than n to the k. Okay, if you think of n as being even 100, okay, it's a big, big, big difference. Okay. So various NP-hard problems and various parameters. Some of them have algorithms like this. Some of them seem not to. Okay, so there's also sort of a subpart of complexity theory where they prove analogs of NP completeness for fixed parameter tractability. So you show things like, if, so for example, clique and independent set is one example, which is thought to not have a fixed parameter tractable algorithm. So you have these things known as W1 hardness and W2 hardness, analogous to NP hardness, such that, if you had an FPT algorithm, it would cause some other collapses which are thought to be unlikely. Okay, so again, I'm not going to talk about any of this, but just know that there's kind of a sort of rich literature out there, which you can see more about in CS 266. Okay. Any questions about that? So that's the first of the 3 problems I wanted to talk about. Okay. All right. So next we're going to visit the traveling salesman problem. And actually I'm going to give you an algorithm which even works in the non-metric case. Okay? So remember the traveling salesman problem is the input is a complete graph, undirected. Every edge has a non-negative cost. Your responsibility is to find a minimum cost TSP tour. What's a TSP tour? It's a simple cycle which visits every vertex exactly once. Okay? And for the general version of the problem, what we saw was that it was NP hard to even approximate it to any factor alpha. Okay? So when we talked about TSP, what did we do? We looked at the metric special case, So we assumed that the edges satisfied the triangle inequality, and then we were able to give good approximation algorithms. We had the MST heuristic, a 2 approximation. We have Christofides algorithm, which was a 3/2 approximation. Okay, so here we're even dealing with a non-metric case. We're not going to assume that the edge cost satisfied the triangle inequality, and we're going to solve it optimally. Okay. Now, of course, it's going to be an exponential time, but again, it'll be faster than brute force search. So if you have n vertices, what kind of running time are you going to get from brute force search for a traveling salesman problem? It's like 2 to the n and factorial, right? So pretty much the feasible solutions are all orderings in which to visit the vertices, and that's going to be a factorial number. And n factorial is a lot bigger than 2 to the n. Okay? N factorial is more like n to the n. It's not quite that bad, but it's close. We'll talk more about that a little later. So n factorial is brute force. And what I'm going to show you next is I'm going to show you a dynamic programming algorithm, which has running time n squared times 2 to the n. Okay? So with n factorial, you know, if you're on your laptop, you could probably handle input sizes with n equal to 12, maybe to 13. You know, and with this, you know, you're still not going to be able to go that big, but you're going to be able to get into the 20s, okay, with this algorithm. Okay, so again, it extends the tractability frontier for this sort of very hard problem. Okay. One drawback to the dynamic programming algorithm is that it also uses exponential space. I guess, 2 to the n space is enough. And brute force search, of course, does not, right? Brute force search is easy to implement in polynomial, even near linear space. And it's actually an open question, whether for the TSP problem or even for the special case of the Hamiltonian cycle problem, whether or not there exists an algorithm with a running time of the form 2 to the n, or even 4 to the n, or even 10 to the n, some constant to the n, and simultaneously running in polynomial space. Okay, that would be nice. We don't know if one exists. Interesting open question. Okay. So that's the plan. And again, sort of the 2 takeaways from this, you know, of this exercise. So first of all, it's another example. It's where it's a famous NP-hard problem, and actually brute force search is not what you're stuck with. You can do better. But also, you know, it's going to be a dynamic programming algorithm. So in principle, you know, it's a little more complicated than the ones you do in CS 161, but in principle, you could teach this in 161. So it's again an example where all the sort of tools in your algorithmic toolbox that you've been developing, they're just useful everywhere. Okay, it doesn't matter if you're doing exact algorithms that are polynomial, faster exponential time algorithms, approximation algorithms, or whatever. Okay. Good. So, how do I want to do this? I want to do a new board. All right. And I'm sure all of you know, last problem set due tonight at midnight. There is no exercise set number 10. Okay, so the final just covers exercise sets 1 through 9. Okay, so algorithm. For notational purposes, let's call the vertices of the instance 1 up to n. It's a dynamic programming algorithm, so there's going to be an array that corresponding to a bunch of subproblems that we're going to populate systematically. Okay? So it's going to be a 2-dimensional array because, as you'll see, our subproblems are indexed by 2 different things. Okay? Now, as you know, sort of in dynamic programming, once you've figured out the right collection of subproblems to study, you know, so that you can solve the bigger subproblems quickly given the solutions to the smaller subproblems, you're pretty much done. Okay, so usually like you're struggling with a dynamic programming solution and then finally it all clicks when you figure out the right set of subproblems. So I'm just gonna cut to the chase and sort of tell you what are the right subproblems that give you this algorithm. Okay. All right, so semantics of a subproblem. So again, there are two indices. On the one hand, you have a subset of V. And then on the other hand, you have a vertex. And in fact, a vertex of S. Okay? So a subproblem is indexed by a subset of vertices, S plus a vertex, J. And what we want to populate this array entry with is the length of the min-cost path. Right, so at the end of the day, we want a tour, but we're going to build up paths. Length of the min-cost path such that it visits every vertex of S exactly once, and it doesn't visit anyone else. So it visits each K in S exactly once. It's going to start at vertex 1. Okay, so all paths begin at vertex 1. And then J indicates the final vertex on this min-cost path. Okay? Ends at J. Now, for this to make sense, it better be the case that vertex 1 belongs to the set S, and it better be the case that vertex J belongs to S. Okay? So S is the vertices that you visited so far. You're keeping track of the start point, vertex 1. You're keeping track of the endpoint, vertex J, but you're allowing optimization over whatever order you want to visit the rest of the vertices of S in. Okay? So that you're sort of not keeping track of. That's what the subproblem is supposed to do. So among all ways you can visit precisely the vertices of S in some order, starting from 1, ending at J, what is the minimum cost such path? Okay? So is the definition of that subproblem clear? Okay. Now, for subproblems to sort of work out, you need a few different things going on. Oh, I should say, so most of the dynamic programming algorithms that you've seen are probably polynomial time algorithms. Right? This is an NP-hard problem, so we're not expecting it to be polynomial, and so therefore, we're maybe not surprised to notice that the number of subproblems is exponential in n. Right? So if you think about S, there are 2 to the n different possibilities for the subset S of vertices. But again, 2 to the n is much less than n factorial, and we were expecting exponential. Okay? So the number of subproblems is theta of n times 2 to the n. N for all choices of J, 2 to the n for all choices of S. Okay, so one thing that better be true about the subproblems is that if we solve all the subproblems, we should have solved the original problem, i.e. the min-cost TSP tour. Okay? But in fact, the cost of the min-cost TSP tour is easy to read off from the solutions of the biggest subproblems, where S is equal to all of the vertices. When S is equal to all of the vertices, this just says what's the cheapest the cheapest path from 1 to J, visiting every vertex exactly once. Okay, so it's a Hamiltonian path from 1 to J. Now, of course, given such a path, it's easy to complete it to a tour. You just insert that last edge between vertex 1 and vertex J. Now, on the optimal TSP tour, we don't really know which J is the one that precedes 1, vertex 1 on the optimal tour, but there's only n possibilities, so we can just check them all. Okay. So this is basically brute force search over the n-1 possibilities for the vertex preceding 1 on the optimal TSP tour. One of these we'll guess correctly. And what are we going to do? So the observation is just that if you think about the optimal TSP tour, of course it has to be an optimal path from 1 to its last vertex J, whatever J is. Okay. And that's what we have computed. And then we also have to take into account the cost of the final edge, CJ1. Okay? So everyone okay on that? So if we can solve all of the subproblems, then in linear time, we can figure out the cost of the TSP tour. Okay? And as usual with dynamic programming, if you want not just the value of the optimal solution itself, all of the usual tricks will work for that, like backtracking tricks, for example. Okay? So questions about that? All right, so if we can solve the subproblems, then we're done. So then really, the final ingredient that we need is we need a way to systematically solve larger subproblems from smaller subproblems. Okay, so that is, we need a recurrence telling us the ways in which larger subproblem solutions can be composed from optimal solutions to smaller subproblems, right? That's the name of the game in dynamic programming. And again, the way I'm presenting this in lecture is kind of the opposite of how one actually does this oneself. So normally when you're trying to devise a dynamic programming algorithm, the first thing you figure out is the recurrence. Okay, you sort of figure out how optimal solutions are composed from optimal solutions to smaller subproblems. From that, you back out a recurrence. Then once you have the recurrence, you can zoom out and say, well, then reverse engineer the subproblems. Okay? So, but for ease of presentation, I'm doing it in this order. Okay, so I'm not going to talk about the base cases when S is just a singleton. Those are sort of easy to handle. So suppose you have a subproblem with at least 2 vertices in S. So again, remember what we want to compute here. We want to compute a path. It visits every vertex of S exactly once. It starts at 1, it ends at J. We don't know what that looks like, but we do know that there has to be some vertex K that precedes J. Okay? And then the path from 1 to K better be optimal. Okay? Otherwise, you could substitute a different, better path between 1 and K, visiting the vertices outside of S minus J, and get a better path from S to J, visiting all vertices at S. Okay? So basically what we're going to do here, so just like in the final output, we in effect guessed what was the final vertex visited before vertex 1 and take the best of all possibilities. For the recurrence, we're just going to guess the penultimate vertex of the best path from 1 to J visiting S. Okay? There's only a linear number of possibilities. We're going to check them all, take the best. Okay? Okay, so what are the possibilities for the penultimate vertex, the second to last vertex on the optimal path? Well, it should belong to the set S. Maybe if you want to think of, let me ignore the case where S equals 2, and then what I'm going to say here is correct. So 1 should be part of S. If S equals 2, then actually if you think about it, the previous vertex is 1. So think of that as another base case if you want. And K should not be, K not equal to 1 is what I meant to write. And then K, of course, should not be equal to J. Okay? So again, what's the point? The optimal solution, by definition, that's the best path from 1 to J, visiting everybody in S. So what are the candidates for the vertex right before J, assuming we're visiting at least 3 vertices? Any of the vertices of S other than the 2 endpoints of the path, 1 and J. Okay? Oh, I guess I should say what this is. All right, so what's the subproblem? Well, you're looking at the subpath that's not visiting J. Okay, so you're going to visit 1 fewer vertex. You're not going to visit J. And we're guessing that K was the penultimate vertex of this path, so the endpoint of the subpath. And then, just like here, we have to account for the cost of the final hop, so of getting from K to J. Okay. So any questions about that? I wasn't planning on formally doing a correctness proof. It's just by induction. So really the question is just, do you believe the recurrence? Okay. Do you believe that it's really true that this left-hand side, the cheapest path from 1 to J visiting S, really is the minimum over all possible guesses for the penultimate vertex K of the cheapest path from 1 to K visiting everybody in S other than J, plus that last hop from K to J? Yeah? Okay. Good. Right, so I guess I should say, in what order do you solve the subproblems? Well, from smallest to largest. So how do you measure the size of these subproblems? Well, you just look at the cardinality of the set S. Okay, so the first thing you do is you handle the base cases. You handle all the cases where S has only a single vertex. Then you handle the cases where S has 2 vertices, then 3 vertices, and then 4 vertices. Notice if you do that, all of the things you need on the right-hand side of the recurrence have been previously computed when you considered smaller sets, so they're available for constant time lookup in your 2D array. Okay. How much time does it take to solve a subproblem? Well, each of these lookups is constant time. It's previously computed. And you're searching over at most a linear number of vertices in S. So linear time per subproblem. Remember, there's n times 2 to the n subproblems. So n squared 2 to the n time overall, as promised. Okay. So any questions about that? All right, so that's an example where we beat brute force search for an NP-hard problem without making really any compromises, other than, I guess, the space blow-up. We didn't look at a special case. We didn't look at a parameterized version like with Vertex cover. We simply had a faster, if still exponential time, algorithm. Okay. And our final example is going to be another example of that type, where it's an NP-hard problem. We're just going to solve it in general faster than you might have expected if you thought all you could do is brute force search. So any questions before the final example for today? Okay. So our last example is going to be 3-SAT, the canonical NP-complete problem. So remember how this works. So there are n Boolean variables. Okay, you're going to be looking for a truth assignment. You're going to assign each variable to true or false. There are clauses. Each clause is a disjunction, that is an or, of 3 literals. Okay, literal is either a variable or the negation of a variable. So a clause just asks for one of the literals to be satisfied by the truth assignment. And in the 3-SAT problem, you look at the conjunction of the clauses. So you want every single clause to be satisfied by the same truth assignment. Okay? Last lecture, we studied the optimization version, max 3-SAT, where the goal was to just satisfy as many clauses as you can. Here, we're just going to look at the more standard decision version that you learned in 154. We just want to know yes or no. Is there a satisfying truth assignment or not? So, what kind of running time is brute force for 3-SAT with n decision variables? 2 to the n, right? There's 2 to the n truth assignments, true or false for each of the n variables, and so you just try them all, okay? Maybe times linear time to actually check if it's a satisfying assignment or not. So that's what we're trying to beat. We're trying to beat 2 to the n, and we'll beat it actually by a pretty significant amount, which is kind of cool. So we're going to talk about an algorithm due to Schoening, which, while not exactly new, at least is newer than a lot of the stuff we do in CS261. It's from 1999 originally. I guess a little context. So Schoening's algorithms for 3-SAT. It's going to be a randomized algorithm, and it's an extension of a previous really neat algorithm by Papadimitriou for the 2-SAT problem. Okay, so what's 2-SAT? Well, same thing, except now every clause has only 2 literals instead of 3. Interesting fact, if you haven't seen it before, 2-SAT can be solved in polynomial time. Okay, so checking whether or not there's a satisfying assignment. Max 2-SAT is again NP-hard, but if you just want to check if it's satisfiable or not with 2-SAT, polynomial time. The classic way of proving that is to reduce it to computing strongly connected components of a suitable directed graph. So that gives you a linear time solution to the 2-SAT problem. Papadimitriou proposed a quite different randomized algorithm and showed that that is also a polynomial time. Okay, so it was only n squared, so it's not really the one you'd use in practice. It was conceptually very interesting. And so Schoening's algorithm will extend the 2-SAT randomized algorithm, which was polynomial time, to 3-SAT. Of course, it won't be polynomial time, but it'll be significantly better than brute force. Okay? So how can you do that? So how can you figure out satisfiability without looking at everything? So here's how you do it. So it's going to be a randomized algorithm. So it's going to be a randomized experiment that we'll repeat a bunch of times, capital T. T, we'll figure out what T is later. Okay, basically the running time is going to be basically proportional to T. Okay. All right, so what do? Well, first, you try a random assignment. Okay, so there's 2 to the n truth assignments, you just pick one at random. Okay, each variable equally likely to be true or false and independently. Okay. Now you repeat the following n times. Or, needless to say, if you ever find a satisfying assignment, you just halt immediately and report yes. Okay? So as long as you have not yet found, right, so if you pick randomly and this is satisfying, boom, you're done. Okay, so what if it's not a satisfying assignment? What do? Well, at least one of the clauses has to be not satisfied. Okay, otherwise you would have stopped. So pick a violated clause arbitrarily. Pick a violated clause, CJ. Now we're going to do, so this clause has 3 variables. We choose from those 3 variables uniformly at random. Okay, so we pick an arbitrary clause, but then within the clause, we pick one of the 3 variables involved uniformly at random from the 3 possibilities, and we flip the value of that variable. If it was previously false, we make it true. If it was previously true, we make it false. Choose a variable of CJ, uniformly at random, flip its value. Okay. And now you go back up to the repeat n times. Okay? So again, you check if it's satisfying. If it's still not satisfying, there's some violated clause. It's going to be a different violated clause than last time, but you're again going to pick a random variable from the new clause and flip it, and you keep going. Now, so there's sort of an outer loop of T random experiments, then there's sort of n iterations of this inner loop, and if after all of these n times T inner loop iterations, you haven't found a satisfying assignment, then you very boldly declare that none exist. And that is the algorithm. Okay? So it's a random search algorithm. You would say local search, but local search, you're actually like looking at an objective function to improve each time, and here you're not doing that. You're just flipping something at random. Okay, so it's a form of random search. And that's it. So any questions about the algorithm? Okay. And let's start trying to understand it. So I'm going to keep giving you better and better running times for this algorithm via sort of slightly more sophisticated analyses. I'll give you either 2 or 3 versions depending on the time. So the first thing to notice is that, okay, so randomized algorithms sometimes can make mistakes, okay? So they have errors. Suppose you feed in an unsatisfiable formula to this algorithm. Will it ever mistakenly call it satisfiable? No. But it only says satisfiable when it actually has a satisfying assignment in its hands. Right? So you're always correct when you say satisfiable. If we handed a satisfiable formula, we're not, of course, guaranteed with 100% probability that this will find one. Okay? So maybe it just goes into a silly, infinite loop, just alternating between the same 2 bad random assignments. So by analysis, what are we trying to do? We're trying to understand what is the probability, where the random coins are the ones flipped by the algorithm. What is the probability that when we feed this algorithm a satisfiable instance, it actually finds one? Or the bad case is, what's the probability it fails to find one when one exists? Okay? So the correctness analysis, we're always going to be thinking about the satisfiable case, right? Because obviously it gets the unsatisfiable ones correct. All right, so consider a satisfiable instance. And if there's many satisfying assignments, pick one arbitrarily, call it A star, okay? So think of this as just an n vector of true-false values, okay? And suppose we have any not satisfying assignment, okay? Call it A. All right, so at any given time in our algorithm, we currently have some truth assignment which is not satisfying the formula. All right, so here's a really simple observation. So for all clauses not satisfied by A, of the three variables in that clause, A must differ from A star in its assignments of at least one of those three variables. A star satisfies all the clauses, in particular this one. A does not, so they differ somewhere on these three variables. Yeah? Okay, so its assignment to one of the three variables of the clause differs from what A star gives it. So what that means is that when we take this clause and we flip the value of one of the variables, there's a 1 in 3 chance, at least, that we pick a variable where A has it wrong, okay, where A star has it right and A has it wrong. And by flipping it, we then make our assignment A closer by one variable to the satisfying assignment A star, okay? Now, it could go the opposite direction, right? It could be that you pick a variable where actually A and A star are the same, and you flip it and you make them different. So that would actually increase the distance between A and A star by 1. Okay, so you have at least a 1 in 3 chance of decreasing the distance by 1. You have at most a 2 over 3 chance of increasing the distance by 1. Notice that the probability might be better than a third, right? So it may be that A and A star differ on 2 or even all of the variables of the satisfying assignment. Then you have a much better chance of bringing them together. But the worst case is that 2 of the variables in A are the same as A star, and there's only 1 which is off. But you still have a 1 in 3 chance of guessing right and flipping it to agree with A star. Okay? So probability at least a third. Flipping a variable decreases the distance, and by distance I just mean the number of variables that are assigned different values. So between A and A star by 1. Otherwise, the distance increases by 1. Okay? Is everyone okay with that? So what are we doing? We're trying to understand in what sense does this random search algorithm ever make progress, okay? So here's a sort of probabilistic progress at every step, okay? It's a little weird because it's not monotone, right? It can go backward, and actually the odds seem against us, right? There's only a 1 in 3 chance that we make progress. There's a 2 in 3 chance we go backward, okay? But that's where the exponential time is going to come from. Okay? It's exactly because of that unbalanced bias. So our progress measure is just going to be, what's the difference between our current assignment A and the assignment A star. Obviously, if we ever have distance 0 to A star, we're done. We found a satisfying assignment. Notice, if there are many satisfying assignments, we just picked one A star arbitrarily, so the algorithm might stumble upon a different satisfying assignment even though its distance is far from A star. That's only good for us. We're only going to basically give the algorithm credit when it actually hits A star, okay, or terminates early, okay? All right. So, suppose the distance between A and A star is k. So k out of the n variables are different. Well, each iteration, there's a 1 in 3 chance we bring them closer together by 1. And if that happens k times in a row, then we're at A star. Okay? Right, if k variables are different, and we get lucky, and we have k iterations in a row where we bring them closer together, at the end of that A equals A star, we have a satisfying assignment. So if A star, different k variables, flipping variables of violated clauses, yields a satisfying assignment, either A star or something it hits earlier. Whoops, in k iterations at most, with probability at least 1/3 to the k. Okay. So this is like the algorithm gets lucky and it just makes a beeline from the current truth assignment A to this reference satisfying assignment A star. Okay? And again, it might finish early, that's fine. Okay? You may notice that, okay, in the algorithm, where's the algorithm? Here's the algorithm. So in the inner loop, we repeat n times. Okay? So the biggest k could be is n. Okay? So to handle all possible choices of k, we repeat n times. Of course, you know, if k is something like n over 2, for all we know, the algorithm's actually not going to find something in the first n over 2 inner loop iterations, but then it gets lucky and finds one later. We're not even going to count that. Okay, so over and over again in this analysis, we're going to actually discard the probability of the algorithm succeeding in various ways. We're just going to lower bound the probability of a subset of the ways in which the algorithm can succeed. Okay? So this is a way it can succeed. If at any point it finds a random assignment that's k variables away from this reference assignment A star, it gives you a 1 in 3 raised to the k chance of finishing within k iterations. Okay? All right, so what is k? So this is just this parameterized bounds. This is true no matter what k is. Okay? Well, what do we expect k to be if we just pick a random assignment? N over 2, right? And actually, by symmetry, the probability that k is n over 2 or less is exactly a half. Okay? Good. For each variable, you have a 50-50 chance of agreeing with A star with it. Okay? So if you look at one of our capital T trials and you look at A naught has distance n over 2 or less from A star with probability at least a half. Okay? So one way this algorithm can succeed is to first pick a random assignment which agrees with the A star in at least half of the positions, and then to n over 2 iterations in a row, get lucky and make the right choice of the 1 in 3 variables to flip in the violated clause. Okay. So these are all the things that have to happen. Okay, so you have a starting assignment where k is n over 2 or better, and then n over 2 times in a row, you make the correct choice, so the 1 in 3 variables. All right? So if this ever happens, then the algorithm indeed finds a satisfying assignment. Okay? All right, so from this, we can back out what capital T needs to be. Okay, so the name of the game here is, obviously, if it's satisfiable, the more trials we do, the probability that we find an assignment only goes up. So the question is, how large do we have to take capital T so that the probability that we miss a satisfying assignment is quite small? Okay, say inverse polynomial in n. Now, it's an NP-hard problem, and every iteration can be implemented in polynomial time, so we're expecting the number of iterations to be exponential. But the question is, what exponential is it? Okay? All right. So what do we conclude? So if the formula is satisfiable, we succeed in T outer iterations Okay, so think of each of this like choosing an A naught and then doing n random flips. Think of each of those as a trial. We have capital T trials. We argued that each trial succeeds with at least this probability. I guess for notation, let's call this P. Succeed except with probability. Well, what has to happen? Okay. So how could you never find a satisfying assignment in any of the capital T iterations? Well, this would have to not happen every single time. Okay? So this not happening, that's just the complementary event. And then this would have to happen T times in a row. And they're independent, so we just take it to the T power. Okay? Oh, I have P here. Yeah, so let's do P. Okay? All right, so how should you think about this? Well, this is easiest to understand if you use the estimate. Again, remember 1 minus P is always bounded above by e to the minus x. We've used that a couple times already this course. So this failure probability is upper bounded by e raised to the minus P times T. Remember, we want our failure probability to be small. What's small? Let's say inverse polynomial in n. So we want to solve for the value of capital T so that this failure probability is inverse polynomial. Okay? And that's easy to do. You just take T equal to 1 over P to cancel that out. And then you boost it by another logarithmic term. And this is not specific to this algorithm, this is just always true. So whenever you have a subroutine which has one-sided error, so it sort of does something wrong only in a particular case, otherwise it's always correct, and you want to boost the correctness probability, this is the relevant derivation. Okay? All right, so so this is 1 over n to the d for your favorite constant d, pick it however you like. When T equals d natural log of n over P. Okay? And so if you plug in this value for capital T here, the P's cancel. You have e to the minus d natural log of n, also known as 1 over n to the d. Okay? And again, so just by setting d however you want, you can get the failure probability to be as small an inverse polynomial as you want. Okay? And so now we're done, because we already know what P is for this algorithm. Right? So this is P. So we want to look at, we just want to plug that in for P here. Okay? So what is this? This is theta. So let me suppress all the constant factors. I'm going to ignore that 1/2. I'm going to ignore this d. So what is this? So this is 1/3 to the n over 2. So we flip that, we get 3 to the n over 2. Also known as root 3 raised to the n. Okay? So root 3 raised to the n times natural log of n. Okay? So to summarize, if we run this algorithm with capital T equal to this, then we'll never make a mistake when it's unsatisfiable. And if it's satisfiable, we'll make a mistake with only probability, say 1 over n cubed. Okay? So in that sense, it's solving the 3-sat problem. Okay? Just makes a tiny bit of error sometimes in the satisfiable case. Root 3, that's like 1.73. So this is already a non-trivial improvement over 2 to the n. Okay? So by doing random search, we really don't need to look at all of the assignments. Okay? You can do better. So any questions about that? Okay. So it's actually quite easy to make this bound even better. So first, let's keep the algorithm literally exactly the same and just prove a sort of better, meaning smaller bound on the capital T that we need to get a low error probability. So the idea is we're going to try to do something smarter than this. Okay, so previously what we said is like, well, you know, if you have a trial and the algorithm sort of screws up and picks a random assignment which is more than n over 2 away from A star, let's just give up. Let's just like pretend like the success probability is 0. So let's be a little smarter about that. So we pick a random assignment. It has some distance k from A star, and then we're going to have some success probability, which is a function of k. Okay? So to do this, we need to have an understanding of, okay, what's the probability of various values of k? Again, k will always be the distance between the initial assignment here and the reference assignment A star. So distance between A naught and A star equals k. So how would that happen? Well, so that means there's exactly k out of the n variables that you got wrong. Okay? So there's n choose k choices for which of the k variables you get wrong in your random assignment. And then you have a 2 to the minus n factor. Okay, so for every variable that you get right, you have to flip the coin and actually has to come up right. For a variable you're getting wrong, you have to actually flip the coin and come up wrong. Okay? So the distance between A naught and A star is k for any k between 0 and n, with probability exactly n choose k 2 to the minus n. Okay? So this is sort of like the same thing as saying, what's the probability that you get you flip a sequence of n coins, what's the probability that you get exactly k heads? Okay. Everyone okay with that? Okay. So let's just have a smarter version of this thing, where rather than just sort of conditioning on whether you're n over 2 or less, let's actually parameterize it by k. So a trial succeeds now with probability at least. Well, so you look at all the possible choices of the initial distance between A naught and A star. We agreed that the probability of a given distance k is n choose k times, 2 to the minus n. And then in the case where A star and A differ in exactly k spots, then the chance that you get lucky and you just make a beeline straight to A star is 1/3 to the k. Okay? Everyone cool with that? So in effect, what we're doing is we're conditioning on the distance between A naught and A star. Conditioned on k, this is a lower bound on our success probability. Then when we remove the conditioning and take expectation over what the value of k actually is, then we get this term. Okay. All right. So I don't know how this looks to you. This maybe looks like a mess. Like, how do we interpret this? But actually, we're pretty stoked to get this expression. So let's pull out the part that doesn't depend on k. So we just get sum over k n choose k times 1/3 to the k. Might start reminding you of like binomial expansions, right? So like a plus b raised to the n is like sum over blah, 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 blah. So actually, with the binomial expansion, we can recognize this as exactly 1 plus 1/3 to the n. Okay? So again, think about expanding this. If you expand all of these products, how many times are you going to get a term of the form 1/3 raised to the k? Well, that means you chose the 1/3 exactly k times. You chose the 1 exactly n minus k times. And there's n choose k different terms from which you could choose those k 1/3s. Okay? So again, this is just the binomial expansion, okay, that you would have learned in 103. Okay, so it's pretty sneaky to recognize it here, but it works. Okay? So this is a 4/3 to the n. This is a 2 to the minus n. So what we have here is, what do we have? 2/3 to the n. Okay? So this is our new p. Our old p was 1/√3 raised to the n. Our new p is 2/3 raised to the n. Okay? So again, just sort of plugging in for what we have to set p to be in order to get our desired error probability. So now we get a running time. So succeed with high probability when t is equal to theta of 1.5 to the n log n. Okay? Everyone cool with that? Any questions? This bound is like the slickest of all of them in a way. So I'm going to show you an even better bound, but this 3/2 to the n is maybe the one kind of worth remembering because it's so nice. Okay. So we can even do a little bit better than this. Okay. Again, we're already kind of blowing away 2 to the n. It's pretty nice. 1.5 to the n is definitely like, you can definitely solve bigger problem sizes than you can with 2 to the n. It's pretty noticeable. But so let's do one more step. So I'm going to tweak the algorithm slightly. Instead of n here, I'm going to make this 3n. Okay. What's the intuition? So like, what are we trying to do? So again, all along we've been sort of analyzing the success probability of our algorithm by like throwing out so many different ways it could succeed, zooming in on just a subset of the ways it could succeed, and even just lower bounding that probability. And so notice we've actually only been counting a success in this special case where you literally move monotonically from your random initial assignment A0 to A star. So if you differ in k spots, you really have to flip, k lucky coins in a row. Otherwise, we just don't count it at all. But obviously another way you could succeed is maybe, maybe once you pick the wrong variable and you go backward. You increase the distance between your current assignment and A star. But then you make up for it by k plus 1 times you pick the right variable. Okay? So that would still be a net movement of k agreements toward A star. So again, you would have a satisfying assignment. So that's just what we're going to do. We're going to also count the ways where you make some mistakes, but you compensate by making a correspondingly larger number of correct decisions. That turns out to give you a better bound. Okay? All right. So how should we analyze this? So an iteration now succeeds with probability. So what we're going to do is we're going to take this exact same expression. Okay, so remember what this was. This was condition on k, the distance between A0 and A star, and this was a lower bound on the success probability. So we're just going to plug in a different lower bound on the success probability now. Okay? And again, conditioned on k. So again, we have k equals 0 to n choose k 2 to the minus n. That's the probability the initial distance really is k. Okay, so now, before we said we're only going to count it if you just make k correct decisions in a row. Okay? So now, we're only going to count it if in the first 3k decisions, you make exactly 2k correct decisions and k incorrect decisions. So again, don't forget what's sort of driving all of this. We're tracking the Hamming distance, the number of different variables between A and A star. We pick a violated clause, at least 1 in 3 probability, they get closer by 1. With at most 2 in 3 probability, they get farther by 1. But one of those will happen. Okay, they'll either get closer if you pick a variable where they make different assignments, or they'll get farther if you pick a variable where they were making the same assignment. Okay? So if you make k incorrect decisions, increasing the distance by k, but you make 2k correct decisions, decreasing the distance by 2k overall, that gives you a net decrease of k. So again, either you find a satisfying assignment along the way, or after you've made those k incorrect decisions and 2k correct decisions, you've decreased the distance from A star to 0. So that's definitely satisfying. Okay? So up there, we looked at the probability that you just make k correct decisions in a row. Here we have 2k correct and k incorrect. So what's the probability of that? So this is, again, a counting argument. So we're thinking about the first 3k decisions that the algorithm makes. We're only going to think about the case where exactly k are incorrect and 2k are correct. So again, 3k choose k. This is sort of the choice of the subset of decisions where you chose the wrong variable. And now it should be the case that, in all the cases where you're choosing the wrong variable, indeed you choose the wrong variable. And remember, that's with probability 2/3 at most. And then for the other 2k choices where you're supposed to be decreasing the distance, you need to see a 1/3 2k times. Okay? So this is just of your first 3k decisions, this is just the probability that exactly k of them are wrong and 2k are correct. Okay? All right. Good. So, I don't know what you think of this. This probably now is really starting to look like a mess. The good news is this binomial coefficient we'll be able to deal with the same trick as before. But now we've got another binomial coefficient, which is sort of annoying. Okay? But whenever you have binomial coefficients and you kind of want to massage them into other things, you often want to expand them in terms of factorials and then use Stirling's approximation on the factorials. Let me just remind you quickly, Stirling's approximation. Again, this is one of those things, the only thing that's important for you to remember is that there is a really nice approximation of the factorial function. You can always look it up on Wikipedia. Just remember that something like this exists. So it's called Stirling's approximation. And what is it? It says that n factorial is up to a constant factor equal to square root of n times n over e to the n. Okay? So the factorial, it's obviously at most n to the n, because each of the products here is at most n. And of course, it's going to be a little bit less, because most of those numbers are less than n. And so this is how much less. Okay, you divide n by e, but it's still raised to the n power. Okay, times a root n. Okay. The constant here is like root 2 pi, but it doesn't matter for us. Okay. All right. All right, so why did we introduce Stirling's approximation? We don't like this binomial coefficient 3k, choose k. So let's get a better handle on that. So 3k, choose k. Well, what is that? That's 3k factorial over 2k factorial k factorial. So using Stirling's approximation, right up to constants, let's just say theta, we have a root 3k here, root 2k here, root k here. Up here we have a 3k over e to the 3k. Down here we have a 2k over e to the 2k times k over e to the k. Okay? Now obviously I wouldn't have done this unless there were going to be some serious simplifications. Okay? So, so equals. So this basically winds up being up to constant factors of 1 over root k. Okay? So let's look over here. Let's look at these things. Okay? Let's start, say, with the e's. There are all these annoying e's in the denominator. But how many 1 over e's do we have on the top? 3 to the k. What power of 1 over e do we have on the bottom? Well, we have a 1 over e to the 2k and then also a 1 over e to the k. So that gives us 1 over e to the 3k on the bottom. So the e's go away. Okay? And again, you sort of get used to this once you've sort of done these kinds of calculations. It's annoying in the Stirlings, but then it cancels out in the binomial coefficients. Same thing for the k's. Okay, so ignore the 3 and the 2, ignore the coefficients, just look at the k. We have a k to the 3k on top. We have both a k to the 2k and a k to the k on the bottom. So those factors of k are going to cancel as well. What's left? The powers of 3 and the powers of 2. Okay, so we have a 3 to the 3k on top. We have a 2 to the 2k on bottom. Okay? So that's the simplification we get. So we're going to plug this in for the binomial coefficient. Okay? And actually, let's do it this way. Right? So let's actually now just sort of throw in the 2/3 to the k and the 1/3 to the 2k. Okay? So let's just write some constant c. That's what was in the theta. And now let's also take care of the other terms that depend on k. So 2/3 to the k, 1/3 to the 2k. So now we get even more cancellations, right? We have a 3 to the 3k here, we have a 3 to the k there, a 3 to the 2k there, so all the 3's cancel out. We have a 2 to the 2k here, we have a 2 to the k here, so we're left with 1/2 to the k, okay? So c times 1/√k times 2 to the minus k. Okay? So that's our estimate for 3k choose k times 2/3 to the k times 1/3 to the k. All right. So let me just sort of rewrite that. Actually, let's just go on. Let's just do it here. Don't need Sterling anymore. That served its purpose. So this is a most constant times sum over k equals 0 to the n choose k, 2 to the minus n, the same stuff we had before. Now I'm plugging in our estimate for this. So there's the constant, there's the 1/√k, and then there's a, is this right? Yeah, 2 to the minus k. Okay. So this is our lower bound on the success probability. All right, so let's start with the square root. Okay, we want a lower bound, so let's just assume that this is always its biggest value. Okay, so let's just replace this by a 1/√n. Okay, so constant over √n. That only gives us a smaller number. We're dividing by more. So now, oh yeah, and let's take the 2 to the minus n out too. Okay, that doesn't depend on k, so let's move that out front. And now we're just left with sum over k equals 0 to the n choose k times 2 to the minus k. And now this we can recognize again as a binomial expansion, just as before. This is now 1 plus 1/2 to the n. All right? So again, think about deleting this stuff. All right, we pulled that stuff out. Looking at this thing, if you expand 1 plus 1/2 raised to the n, this is exactly what you get, binomial expansion. Okay? All right, so what do we have here? Theta, well, so this is a 3/2 to the n. That's a 2 to the minus n, so that gives us 3/4 to the n. So theta of √n, sorry, 1/√n, 3/4 to the n. Okay? So this is our new p. Okay, we had a p at one point, which was 1/√3 raised to the n. Then we had a p which was 2/3 to the n. Now we have a p which is 3/4 to the n. And again, remember our running time is basically the reciprocal of this. So now t equals theta 4/3 to the n times √n times log n is enough. Okay. So brute force search gets you 2 to the n. Random search gets you 4/3 to the n. There are some minor improvements on this known, but I've actually gotten you pretty close to the state of the art for worst case running time bounds of exact algorithms for 3SAT. Okay. So any final questions? All right, see you Thursday for the last lecture.